So let us start with the first problem for the day. Let's go through this nice problem where we have to find out the equation of the path of the ray. Let me read the problem for all of you. The problem is that there are large number of thin converging lenses, as you can see, and each of them is having a focal length of f. They are placed back to back, and the distance between consecutive lenses that is given as L, right? There are some conditions which are given, like the distance L is negligibly small as compared to the focal length F. And the problem is such that there is a light ray which is coming parallel to the principal axis, okay? And let's say it hits the first lens at a height of h with respect to the x-axis. The question here is to find out the equation of the trajectory, right? We need to find out the equation of the trajectory of this ray, and let us treat this location as the y-axis. This is how it is. So there are some conceptual points we will use in this problem to find out the equation of trajectory, and for that, what I will do is, let me treat a general location. Let's say the ray has already tilted. Let's say while passing through these grid of lenses, if the ray has already tilted by some angle theta, I want to analyze for the motion of the ray in that span of dx, let's say from x to x plus dx. If I enter from this point and I am forming an angle of theta with the horizontal, by the time I come out of that thickness dx, I'll further deviate. That means the ray will further deviate by some angle d theta. So what will come out will be a ray which is traveling at an angle of theta plus d theta. We are yet not known. I mean, this is the origin, x-axis, y-axis. Obviously, I am interested in y versus x of this ray. So we don't know about the path, but we know that whatever path it will follow at some general x for some general xy, if it is traveling at an angle of theta and it further shifts by d theta, the total angle that this ray is making with the x-axis there, that is theta plus d theta. I want to find out the equation of this trajectory. I'm saying this is the general point here, which is, let's say, P. So let me write one equation for the slope of this ray, which is dy by dx. That will be equal to tan of minus theta. So tan of minus theta. So that term for me is minus tan theta. And let me write it as some minus theta. So I need to eliminate somehow. I need to somehow find the expression of theta in terms of y and x to finally report the result. One thing that all of us know is, for n lenses which are kept back to back, you know that 1 upon f equivalent, that can be written as the power will be added. So basically sigma over I, 1 upon fi. Now what I am trying to say is, while you are traveling that distance dx, so try to understand this thing, that I am trying to analyze this problem for some x to x plus dx. So I am analyzing that section dx. And let me find out the equivalent focal length of the net lens in the thickness dx, in dx, right? So in dx, whatever be the number of lenses, I want to replace those lenses by a single lens, and I want to find out its equivalent focal length. So technically, I should be writing 1 upon f equivalent in that dx to be equal to these 1 upon f terms. And the only catch there is, you need to write those number of terms of 1 upon f in that thickness dx. Now he has already given, if you read the problem carefully, he's already given that they are separated at distance of L. So in that distance, dx, total number of lenses. So let me multiply this by dx by L. Just check this carefully. Once we get that term dx by L, that dx by L is the number of lenses which are in this thickness, right? So 1 upon fk utne terms, those many number of terms will be there. So once you get 1 upon f equivalent, now I can use my second equation, which basically talks about the deviation of the ray through the effective lens. And I can simply say that if I am hitting this at x comma y, if the coordinate of this point, that is x comma y, general point P, you can simply say by that result delta is equal to h by f. You can say the deviation that will happen here, which is d theta, should be written as y upon f equivalent or f net, whatever you want to say. That d theta will be equal to y upon f equivalent. Now things are simple, because by virtue of these two equations, I will have d theta is equal to y, and that 1 upon f equivalent is dx upon f into n, dx upon f into n. So maybe that is equation number 3 for me now. So I know the expression of d theta. I know my term dy by dx. So now I think it can be easily solved, because from these two equations, I want to eliminate that term theta. So seems like it is d theta by dx is coming out as y by fl, and theta itself is dy by dx. Now theta itself is minus dy by dx. So it comes out as minus d2y by dx2. That's what we get. Minus d2y by dx2. So now it is simple calculation, because that means d2y by dx2 is coming out as minus 1 by fl multiplied by y. This is my core equation, and that means it is kind of a second order linear differential equation. So treat this term as kind of omega square. So you'll have d2y by dx2, that is equal to minus omega square into y. So I am directly writing the root of this equation. You can treat it as an equation of SHM also. There it is d2x by dt2 is equal to minus omega square x. And instead of t, we have got a x here. So I can simply say the root is y is equal to some a sine omega x plus some constant, call it phi. That should be the result to the problem. Right? Omega is known to me. So there are three parameters here, omega, phi, and a. I think easily you can answer this. Omega is 1 by root of fl. And for a and phi, I think initial conditions are given, like x is equal to 0. So I think h is a sine phi. And not only this, the slope is also 0 there. That is at x is equal to 0 when the ray entered here. The slope is 0. So that 0 will be equal to a omega cos omega x plus phi, x is equal to 0 cos phi. That's fine. So I think omega known, phi comes out as pi by 2 finally, and h comes out as a. So amplitude comes out as h. So a is known, phi is known, omega is known. This is the final equation that will give you the answer to the problem. So just to recap the concept, what was there in the problem? The problem setter is using the concept of delta is equal to h upon f. That is one thing that he has used. Delta is equal to h upon f. And secondly, to write the equation of the curve, we have used a bit of calculus, and finally we got the result. This thing is clear to all of you when you talk about 1 upon f equivalent in a given distance dx. And I have written the number of lenses in that dx distance as dx upon n. So that will give you the result. On a spherical planet, the refractive index of the atmosphere as a function of altitude h above the surface, that function is given to you. Indirectly is saying that the refractive index as a function of height, that is some n naught upon 1 plus epsilon h. Right, this is given. N naught and epsilon, they are constants. Problem is somewhat like this, that if you hit a laser beam, a horizontal laser beam, at an arbitrary altitude, you need to prove rather that if that laser beam follows a trajectory that encircles the planet, if this is given to you, then we need to find out the radius of the planet in this case. I mean, first of all, if we go and analyze in the problem, how is this possible? How is this possible for the ray to encircle the planet at whatever height where it is incident? If you find that out, so I will just draw the structure for you where you can start thinking on the problem. Let's say this is the surface, radius r. I am talking about position which is at some height, let's say h. Let's say this is the location where I'm discussing the beam. And it has got a height h. So what I'm trying to do now is I want to analyze it. Let's say this radius is r, this is h, and let us try to analyze it for a small gap which is a dh, right? And basically I want to use Fermat principle. If a beam is there at h and it is encircling the center of Earth, treat this point as center of Earth, and try to look into the concept through which the phase moves. I mean, look into this wavefront and try to think that if there is a point here at h plus dh and there is a point here at h, how the phase will move such that it encircles the center. Right? Now, in fact, if while you analyze the movement of phase, you do it through the concept of optical path length. I'm just writing one thing and let us see how we compare it. What I'm saying is, if you are sitting at this h, right, we understand that when we write the optical path length, and I think all of you understand why we use this concept also. So optical path length, if you're converting everything into air, absolute medium, that is perceived as the absolute refractive index mu into the distance that it travels. So I'm thinking in terms of mu into distance. And if I want to write optical path length for a particle on that wavefront, that can be written as like if this guy travels some angle, maybe a d alpha here, and I'm sitting at r plus h, and I'm analyzing it. So I see that, and remember one thing, this arc length, because it has to encircle, this is very, very small. So over that d alpha orientation, indirectly he has traveled an optical path length which is equal to r d alpha. So like r plus h into d alpha, r d theta types, and into the mu term here. I'll call this point 1 and this point as 2. So basically mu1 into r plus h into d alpha. And the point is, the other person, which is, this is optical path length of 1. If I want to write the optical path length for 2, I think it should be mu2, mu at that location, into r d theta term again. Seems like r plus h plus, this is dh to dh, and whole multiplied by d alpha. That is equation number 2. And we understand, for them to still remain on the same normal, you understand this point, that if all of them have to remain on this normal again, so optically, the optical path length of these 2 points should be the same. So whatever they have traveled physically, you understand this point, that I'm just not taking the physical or the geometrical distance. I'm looking into the optical distance. Indirectly, I'm looking into the phase, or you understand the time. Optical path length बोल दो या phase या आप बात कर रहे हो time की, it is one and the same. So I've written the optical path lengths for both of them. Now it is simple. If we can justify that optical path, for them to move in a circular path, if optical path length 1 becomes equal to optical path length for 2, my purpose is solved. That makes it mu1 into r plus h into d alpha is equal to mu2 into r plus h plus dh into d alpha. This term will obviously cancel out. And remember, the mu's that we have written, that mu1 is indirectly mu at r plus h, and this term is basically mu at r plus h plus dh. This is mu at r plus h plus dh. Now this equation helps me out in the problem. Mu r plus h and mu at r plus h plus dh into r plus h plus dh. So indirectly it looks like if there is mu at r plus h, and that height I am writing as r plus h, and basically if you treat this guy to be some function of h, what we are trying to say is the change in that function is 0. So if I'm treating this as some guy g of h, you can say, that's why while you are writing the function again, so you're writing mu at r plus h plus dh, and the second term that you have written is r plus h plus dh. If they are equal, indirectly we are trying to say that g prime h should be equal to 0. So that is how I have taken up this equation here, and then I have written this. Now I think it should be straightforward, because that makes it d by dh of this function g, that should be made equal to 0, and from this we are searching for a value of r. Now substitute the result there, that n as function of h, remember this n as function of h or mu as function of h is given to you, which is n naught upon 1 plus epsilon into h. So just solve it out. I think now it is simple. Mu at r plus h, and gh is known to you, and just differentiate and make it equal to 0. See what is the value of r. I think r you will get from this equation. So let us substitute it and let's see what comes out. So it is r plus h, that can be written as at h is equal to 0, that value is given as n naught, right? And I think this term can be written as, for smaller heights, I'm taking some approximation here, and then we will justify also. So this comes out as, if h is small, this is like n naught into 1 plus epsilon h raised to the power minus 1. If this term is small, so I'm just taking that approximation, this will be equal to n naught into 1 minus epsilon h, and then it becomes n naught into 1 minus epsilon h into r plus h. N naught into 1 minus epsilon h into r plus h. That term is coming out as 0. I'm talking about heights which are small. And I think now if you differentiate, n naught is taken care of, r is gone. So you are if you are solving it for a smaller height, I mean, this equation being satisfied for a h which is not large in comparison to the radius of Earth, assuming that you will get a value of h. And if you sort out this equation, well, just check what is the relation between that r that you need, what is that r which you are getting. Problem will become very straightforward also. Another way is also there to look into it. But this was one straightforward way of looking into the problem. I'll just explain the concept to you and then we'll go back to the equation final step, which is now simple. I have only used this basic concept that if I want this rate, I indirectly use Fermat's principle to solve. If it is at a given h and we want this beam to encircle, what we are thinking is, if there is a wavefront which is here, which is along the radial direction, and all these particles are moving on it, after a differential displacement, I have made the orientation of the wavefront identical to the previous orientation like this. And then the same concept follows as such for every d alpha, d alpha, d alpha. So it will keep on encircling the Earth, right? So for any h where you want to hit this laser beam, we are trying to solve it for a general h where this laser beam is incident. And for that thickness dh, I want it to encircle. So Perikal said that thing becomes evident to you that you have to just write this equation. And then I knew that this term should be constant. So I just said that d by dh of that expression should be 0. Presuming, which is given also according to the question setter, it is not large in comparison to the radius of Earth. So using that data as such, I have taken my n, or simply you can take the basic expression also and just differentiate that term and take it equal to 0. That equation will help you finding out the value of r. Another way of looking into the problem, I'll explain that. If you are close to the surface of Earth, instead of Fermat principle, somebody can also observe it in another way. Just look into it. Let's say we are close to surface of Earth and we are considering a beam. Later on, I will take this distance as r plus h or whatever you want. But ideally, I mean, we are considering something to move tangentially here at that r plus h. And as it is about to go out, right? If this happens like this, I mean, something that you want to move in circle. Let's say you want to analyze a beam which is moving in a circle. Indirectly, I can break it down into pixels and I can observe it like a polygon, right? These are the small d thetas for which it is moving like this, right? Those small patches where it seems like reflection is taking place. Ideally, it is like that only. This reflection happens, this reflection happens. And basically, at every interface where it is trying to move out, I mean, if I'm sitting here and I went to this point, and this is a new location where it changes. So if this height was, let's say, r plus h, and this radius is r plus h, this is also r plus h, and I've moved out, I went to this place, this guy is, let's say, dh, and I reached here, and reflection happens, right? Reflection happens here. So now the point is clear, na? If that, I have shown these angles to be large, but remember, if this happens for this stretch, this small interface or this small angle, then the same phenomena is going to repeat as such. So, and when you are reaching this place, indirectly what we are trying to say is, you are hitting a new refractive index there. So it seems like if this point is 1 and this is 2, like for me it is more of mu2 at that place. And when I'm taking TIR, just for the boundary condition, I will take this as sine 90 at that place, right? At that location for mu2, for TIR to happen. And that is equal to mu1 into. Now, with respect to that normal, I'm taking that angle, and that angle can be taken as, if this is some d alpha type of angle, I can write that as some d alpha And then finally, I can also say that 1 corresponds to R plus H, mu at R plus H, and 2 is corresponding to R plus H plus DH. So that mu1 and mu2 that you need, that I can write. Just try to understand that this analysis has been done for a small angle, and there the radius has changed by a small amount, which is DH in that context. Now, if you apply the Snell's law at this location and use this condition, try to understand that this analysis and this equation is conceptually the same. By saying this point that mu into R plus H, that mu into R plus H, that term comes in sin d alpha term already. Just observe that d alpha term and you will get your result as such. I think that idea is clear to all of you, na? Now I'm not looking into, I am just trying to observe that when this ray reaches this point, it will become tangential there. Somebody can say that I have shown it as a TIR already here. That is only because I am just above that angle. So that's why at that location I have taken this. And the previous one, I think this angle here, previous angle, this is 90 minus d alpha. So in same context, if I'm very, very close, so I will write it as a sine of 90 minus d alpha. And that cos d alpha, I'm going to write as, it is clear to you, it is R plus H. So that third equation I'm writing as cos of d alpha, which is R plus H upon R plus H plus DH. Right. And then this term becomes mu at R plus H, and the second guy mu2, that is mu at R plus H plus DH. You can understand by all these three equations, that has become sin 90 minus d alpha. So I've taken cos d alpha directly. That angles were different. So finally, what I'm getting again is mu at R plus H into that R plus H is actually mu at R plus H plus DH multiplied by R plus H plus DH. Observe it carefully. Remember, this angle I had taken as d alpha, so this was 90 minus d alpha. So for the previous interface, with respect to the normal there, it is 90 minus d alpha. I could have written it as some d alpha prime also, or d beta you can use, so it doesn't matter. Ultimately, what I have come, this is method 2 of look, this is the basic Snell's law through which I am commenting on the same. That is possible only if this equation is being followed. So whichever R, you bombard your beam, you want to have this. And remember one thing, as a special case for the problem, he can say that this is happening very close to the surface. Now, at what H is it happening? That is not my concern. That he will provide you. I am saying if it is happening at some H, but for it to encircle between R plus H and R plus H plus DH, this is the core equation which needs to be followed. An implication of this equation in the problem is more of this derivative term which I have written, which will yield you the value of H where it happens. And if H where it happens is R, then you will also get the value of R. So that is how, these are the two methods of looking into the same problem.
In this question that we were talking about, in the question he has mentioned that for any height h, right? But when we solve the differential equation, we get a particular value of h. So how does that relate? Because if we, I cannot change the value of h over there, right?
So then now the problem, you can convert this problem. You have to justify now. That's what I have said previously also, that if you want this relation to hold for every h, he has said that mu as function of h. I think I can directly comment on that. What is mu as function of h? What was mu?
Mu is equal to n naught by 1 plus epsilon h.
It was n naught upon 1 plus epsilon into
Epsilon
h.
h, right.
So if it is n naught upon 1 plus epsilon into h, for every h this is happening. Is that given? His only concern in the problem was to find out, his concern in the problem was, what is the radius of the planet at any, actually there is an assumption in the problem, to be honest, what he is trying to say, at any altitude from the surface which is not large in comparison to r.
Okay.
That is how the problem is. At any h, you are solving this problem which is not large in comparison to r.
Okay.
Then, obviously, the equation that you have written is going to work.
Right.
Also, I think you can directly also comment here. This equation, assuming any h which is not large in comparison to r, can we directly from equation also you can tell na? Kya lagta hai, what should be the value of r? What do you think should be the value of r? Because this relation actually helps me out in the problem. You can write it at surface only and just above the surface. Make it simple here. So you just try to write this expression exactly at h is equal to 0 from the surface and just dh above it. I think it will be more easier to look into the problem because this result is applicable everywhere. Na? So if you are interested only in the value of r is your interest, and already you are saying that it doesn't depend upon h. So I'm saying the first h that I'm writing 1, 1 every time, that to take as r, and the second instead of h plus dh, take r plus dh. So think in terms of h, but you substitute things which are simple for you. So when you have to write here, you just have to write that mu at r and r term h is 0. And then this is mu at r plus dh, and this is r plus dh. And then you will get the value of r.
In terms of the h?
In terms of these constants, I think, and not an epsilon. It should not, h will not come there. Na? Dh will cancel out. And you'll get your result, right?
Right. Sir, and you were also saying about how we can relate phase with the optical length.
Yeah.
Could you just repeat that concept once again?
Actually, the complete concept of optical path length, while you are writing optical path length, what we are trying to explain, when a wave is traveling through a particular medium, right, we understand that when waves interfere, when we have to combine signals at a particular location, you look at your signal in terms of time gap. I mean, you can say time gap, somebody can say phase gap. Basically, what I was trying to say is, let's say this is the medium through which a wave is traveling. Now, when we say that I want to analyze this wave at some instance here, actually what we do is we find out the time for which it travels through this medium, and then we presume that if it would have traveled in air, what distance it would have traveled, and that you call upon as optical path length. How I think in these problems is, I always say that it is only about time that you are moving, and time is something which is directly dependent, or phase and time are directly proportional, kind of. If you look into a particular location, if you look into the phase, that quantity at a particular location only depends upon the time. Somebody can say it is omega t minus kx plus phi, but if I'm sitting at a unique location, phase for me is only the time spent, the t time, the phase difference at a particular location is dt for me. So that's what I am trying to say. If you tell me that you will write the optical path length, what I will see is optical path length. Writing optical path length is basically equating time only. That's what you are doing, because you knew that the refractive index is going to change. So for that refractive index, you are changing the length. Basically, you are trying to find out the time there. You are trying to find out the time here, and you are equating the time for this curve and this curve. Then they will be on the same wavefront. Then people say through Huygens principle that they will be in the same phase if they are lying on the same wavefront. So for them to be on the same wavefront, they should be in same phase. And for them to be in same phase, they should have traveled for equal time. And for equal time, you are trying to compensate the change of medium through optical path length, and you are equating the optical path. Ultimately, you are also thinking about the time spent. Read this problem carefully. In free space, a particle is projected from a point P. Particle is projected from a point P on the axis of a fixed rigid cone AOB. Now, the angle at which, actually these are two, this is a conical mirror kind of stuff. This is reflecting face. This is like same. This is the axis of the cone, and these are the reflecting faces, right? So somebody, there is a ray which starts, what he has written, a particle. Okay. So think of it like a laser beam. I mean, there's a beam which is thrown here, bombarded at an angle of alpha, and the distance from where it has been projected or impinged, that is x. This is O, this mirror is B, this mirror is A. So there are a few things we need to answer. The question is, if alpha is 37 and x value is 10 centimeter, beta I suppose is given. So beta is 20 degrees. So what is the question we need to answer? What is the distance of closest approach of that beam with respect to the apex of the cone? And you have to also find out the number of times the beam will get deflected. The number of times the beam will get deflected. So ultimately what we are trying to do here is, like, this beam goes, hits, then it comes here, it reflects from this place, and this keeps on happening by law of reflection, it carries on. So if you need to find out the number of times it will get reflected. Now, the only idea in this problem is, instead of reflecting this green ray or the beam, you better reflect the mirror only. So we observe it like this. If this is my first reflection here, now this beam gets reflected. Now think that if this angle was beta by 2, this is also beta by 2, you reflect the lower surface up. So you take this surface up, the lower face, and this will again make an angle of beta. So instead of analyzing the green ray getting reflected, you analyze this mirror reflection in that surface, in that mirror, and let your ray move straight. Let your ray move straight. Let it move straight. So basically the analysis in this patch is similar to this analysis. It will be at the same distance with respect to the apex of the cone. Now again it will get reflected from here, right? And again it will come close. So instead of this reflection now, that means instead of this reflection here, now you reflect the nearest face again, and let your beam move straight, and let it reflect again by beta, and let this carry on. So basically this becomes simple now. If you have to find out the distance of closest approach, so I knew this thing, that I'm not letting my beam to get reflected. I will let it move straight, and I will keep on reflecting the faces. And shortest distance is the perpendicular distance. So as far as A part of the problem is concerned, that will come out as x sine alpha. Easily I'll get my answer. And secondly, I had to find out the number of times the reflection will happen. Remember, he can also talk about other parameters. I'll answer those parameters when it will go close. So we'll look into that. But let me first answer how many times will it reflect. So we understand that it will keep on reflecting till these reflected faces have made angle which is greater than, now this angle here, what is the value? Let me take the value. This angle was 37 degree. So this angle is like 180 minus alpha, and let them make The first reflection happens at beta by 2. The second is happening at beta by 2 plus beta, and this keeps on happening till my angle exceeds 180 minus alpha. After that, the reflection will not happen. So just check how many times is it getting reflected, because that pattern everybody can see. So it happens first at 10 degree. This value is coming out as 10. That is happening at 30 degrees. So 20 intervals are there, right? So while the sixth collision is happening, how much has it traveled? This value is coming out as 180 minus 37. This is 143 degree, 143. And 30, then 50, 70, these things keep on happening. So 150 is one of them, and 130. So obviously, there will be an angle which is 130 degree. So 5 more collisions will happen. So my 7th collision is happening at 130 degrees. So next would have happened at 150, but that is not possible. Because you understand that while you will keep on reflecting these faces, there will be an instance when this face will be either parallel or even at a higher angle, so it is not going to be reflected. So that's fine. Now, third thing that, how many times will it collide? So we can answer that. 7 collisions are happening. Each is or like exact path. When we say that it is at the shortest distance, he can directly ask that while these collisions are happening and while you are at the minimum distance, that minimum distance happens between which 2 collisions? So the collision number between which the guy is at minimum distance. So that I think all of us understand. We understand that so I'm not drawing on scale now. I know when I'm talking about C part of the problem, I know all of us understand that this is the path for the ray, and this angle is coming out as 90 degree. Alpha here was 37. So while it is crossing this orientation, right, your mirror, this angle becomes 53 degree, that's normal that I have drawn. And before that, beta by 2. So beta by 2 was 10. So one orientation was 10 degree, then there was an orientation of 30 degree, and then there was orientation of 50 degree, and then the next orientation. So between third and the fourth collision, this happens. A lot of other things he can ask. He can talk about the coordinate where it was, and by reflection, I can also let you know the coordinate. Like in this case, I have told you the collision numbers between which this happens, and so on and so forth. So these are 2 straightforward questions that he is talking about. Definitely he can make some comprehension and he can talk about other things for the ray also. I think you will get your result from this point.
Sir, I'm sorry, could you explain the C part once again, please?
Second part.
C
part. See, in C part, what I said is, as the collisions are happening here, like first collision happened here, second collision happened, third happened. So I just wanted to inquire that as this beam is moving, this laser beam is moving, the distance from O keeps on decreasing. And then there is an instance after which it will increase and it will try to come back, right? So actually, whatever happens here, 1 to 2, is identical to what is happening here. So I won't analyze the problem there. I'll look into it here on. Similarly, while it is moving from 2 to 3, let's say this point is 3, I am simply saying let the ray move like this, and let us think that these are the 2 conical faces, like here. So this movement is absolutely identical to this movement. Maybe
Right, sir.
we have not drawn on scale, so you may seem, sir, it seems like going far, but actually if it is coming close, that guy will also be coming close. So that's what I was trying to say, ki as you see this perpendicular, na, one interaction is just below this and the another interaction is above it. Those two interactions are basically the actual interactions happening here. So I said this categorically 53, na? So between 50 and 70. So 10, then 30, then 50. Between third and fourth. Right, between third and fourth, it will be at the minimum distance, and by the time fourth collision will happen, already it would have started to move away, like something of this sort maybe, and then further fifth, and so on and so forth. So while between third and fourth, this will happen, that it will be at minimum distance, and by the time fourth collision happens, already its distance from that corner has started to increase.
Okay, so we can equate the progression which you're getting, the value of that term, until it becomes equal to 63 degrees.
Yes,
sorry, 53 degrees.
53, yes. That's what I'm saying. Because 53 is that normal orientation, but because collisions are happening at 10, 30, 50, 70, so hypothetically we can think that 53 is also orientation, but their collision is not happening. But collision has happened at 50 and 70. So between 50 and 70, the distance was minimum. Right?
Okay,
that is
right, sir. And can we find out the distance from the apex at the how much that value that minimum distance is?
Yeah. Like, are you talking about the minimum distance or specific distance?
At the minimum distance, sir.
Didn't get you.
The minimum distance from the apex.
Basically, I can write distance at any point of time you wish. Like, if you want me to write the expression of distance at any t is equal to t, I can write, because simply I have to follow this curve only at that t instance, because he has given me some velocity. So at that t, assuming nothing happens, I will let my particle move on that curve. I will write his coordinate, and whatever is the distance of that coordinate from O is also the actual distance here.
Okay.
So it works. It works for any t is equal to t. So I will get that. Just take up this question number 9. A fundamental problem, read it, where he has used the concept of radiation also. So let me just read this problem. There is a wide homogeneous beam of light. So I'll draw this setup. This is my concave mirror, right? ये रखा हुआ है concave mirror. And now there is a cylindrical beam which is bombarded on the concave spherical mirror of radius r parallel to the optical axis, right? Parallel to the optical axis. Now what we are doing is, you put a opaque disc somewhere here. You put an opaque disc of a small radius r. Remember, the radius of curvature of this guy is capital R. His radius is small r, and small r is small in comparison to capital R. Let's read what is the question now. अब कहता है कि this disc is made up of perfectly heat insulating material. It is placed at a distance of r/4 from the pole of the mirror, perpendicular to the optical axis. ठीक है भाई, this distance here is capital R/4. This is capital R/4. Now what does he want? He is saying, in the steady state, both the surfaces acquire different temperatures which are slightly higher than the temperature of the surroundings. And what is that difference? Delta T1 and delta T2. So can we find out that ratio delta T1 is to delta T2 in the steady state? So question is to find out the ratio delta T1 is to delta T2 in the steady state for the given problem. Basically, we have to use the concept of solid angle also. I think that will be also utilized while solving the problem. But core idea I will give you what is happening. So let me draw the figure here. Now, यार बीम का जो भी पार्ट है जो r रेडियस पे जा रहा होगा, so if I look into the left hand side, so whatever is incident here, that part is clearly opaque hai, so it will be fully absorbing the radiation which is coming from this side, right? And as far as the other segment is concerned, because the radii of the beam that was also given, there was that opaque disc is placed. He has given you that that is a wide beam. Okay, so that guy will hit this body, right? And now we want to consider those rays which will impact the right hand side. Now, because all of them are coming parallel, if I would have drawn it separately, I would have given you a clear picture. This beam would have entered this point F, which is at a distance of r by 2 here. And you understand that you can only consider those people who are above this radius, which is small r. Treat this as small r, treat this value as small r. Consider only these people which are above this. Because uska niche wale to will be absorbed by the left hand side. Now, technically, if nothing would have happened, they would have all reached this place, right? So, all the radiation which is above this place also will finally reach this place. Now, what we are interested in here, if they are coming back from this height small r and hitting it at r by 2, and you sit at the midpoint, right? You sit at that midpoint, which is that location r by 4, then what will be the observation at that place? So just tell me that what is the section of energy which we have to consider जो right side पर जाके hit कर जाए. Just you have to consider that. And effectively, finally, what I am trying to do, whatever power, I will assume the intensity to be some I. Then I will try to multiply, I will do all the things, but let me explain the theoretical part. So then I will try to write the power which is incident on the left hand side and respectively on the right side. And I will equate it by E sigma A T raised to the power 4 minus Ts raised to the power 4. Then I will take the binomial approximation to write that T raised to the power 4 term deficit, like we do in Newton's law of cooling also. Right? So check this part. Directly, I will write few things there. The thing that you have to consider your beam, which is sitting at r by 4. Just observe it. This is r, this distance is r by 4. Take this distance also as r by 4 and just try to draw that boundary ray, like the boundary ray or the beam, whatever you want to say. So this is one beam which is hitting, which is coming here. So anything which is between these two people, like anything which is between this and this is the segment, which is actually going to impinge on this. Okay, जो इसके ऊपर है, that will come from top. So all the flux which is entering between the upper side and this radius r, that all flux is going to hit the right side here. That's what we are seeing. So if you directly tell me that, and let me also write this radius is small r, and I'm treating this height as, let's say, h, right? So now the only thing that I have to write is that value h. So it was r by 4 and twice. So for me, it comes out as twice of r. Simple. And now, if you look into the cylindrical beam and intensity being I, so now all this green flux, you can say, is all going to hit. So whatever is the intensity I into pi, that term 2r square minus r square, that works. So that is the intensity which will be finally deflected from the mirror on the right hand side of the disc, right? And if you look into the left hand side, the same thing is I into pi into r square. And now let me try to write these terms. If I want to write the ratio, so I am saying I pi r square upon I pi 3r square. This power is equal to what it is effectively radiating per unit time. So that is now E sigma A T right side raised to the power 4 minus T surrounding raised to the power 4. Now just you have to observe right side or left side. This is left. So T left raised to the power 4 minus T surrounding raised to the power 4. And this is E sigma A again. T right side raised to the power 4 minus T surrounding raised to the power 4. This E sigma A cancel out. This comes out as 1 by 3. And now I think all of us can directly write. He says the ratio, the temperature difference. So T left you write as T surrounding plus delta T1. And T right you write as T surrounding plus delta T2 and take binomial approximations. So I think this point is clear to you that basically this will come out as delta T1 upon delta T2. So that will also be the answer to the question. The ratio delta T1, delta T2, that will be 1:3. And I'm assuming this aperture height to be large enough for, I mean, anything which is greater than twice of small r. And because small r is given to be very small, then whatever I have said here is perfectly fine under those conditions. So no need to further analyze this problem.
Sir, in the denominator, how did you get 3r square, sir?
In the denominator, I got it from here, na? This term was I into pi into 4r square minus r square. So this was 3r square. So this term I have written here, right? And for the left hand side, I have written
that is the amount of effective area which the flux is affected.
Yes. So I'm taking the intensity incident as I in the beam. Whatever area is exposed by that wavefront, I'm multiplying that with the exposed area. That gives me the energy per unit time. So basically, this in the green section, the energy per unit time is this green value. And this reflects and comes back on this surface. That is energy per unit time. And on the left hand side, I have directly written intensity into pi r square because that will directly bombard the left hand side. And now energy per unit time, which is the power which is hitting the surface directly or after reflection in steady state, whatever power is incident and whatever is the power radiated from that surface, from that side of the surface, will be equal because it is steady state. And what is power radiated? So by Stephens-Boltzmann law, the power radiated is E sigma A T raised to the power 4, and then I have taken the binomial approximation. Fine. So I think we'll finish off the class here, and I'll see you in the next classes soon, right?